Okay, so that was all extremely abstract. We were dealing with kind of a general probability distribution based on which we define this general Q function. So I think it's helpful to look at some specific cases. And when we see new cases, we can kind of use these examples as reference. So the first example we're going to look at is a mixture model. So that is a model where we have z of n. This is going to be a value in 1 to k, and then we have some observed values y of n. This is a real vector. So in this case, for this problem we're looking at here, this is going to be a vector over two values. So this is a vector in r square, or r to the 2, and y depends on z of n. And in this case, we're using k equals to 2. So again, we're imagining that z is unobserved and y is observed for a bunch of examples n in 1, 2, big N. So this is our mixture model. We might want something like this, where we find that there's these two clusters, k equals 1 and k equals 2. And that y given k equals 1 is this distribution here, defined by this oval, and the other is this one. By the way, we're going to imagine that y of n given z of n is distributed according to a normal distribution with some mean and variance defined by z of n. So in this case, we have two clusters, so we have two mean and variance values. And actually, I should, because this is a multivariate observation, we have a covariance matrix, not just a variance parameter. Okay, I think everyone's pretty familiar with this problem of kind of clustering. I think it's worth being pretty explicit so that we can see exactly how the sort of mathematics we developed map to this problem. Okay, so here's our problem. Let's see how, when we apply that EM framework, what happens when we put in this mixture model case. So we're going to need to figure out how to carry out those two EM steps, the E step and the M step. Let's do that. So here, let's start with the E step. In the E step, we have to define our auxiliary Q distribution, which is P of z given theta t. We can figure this out as follows. Here we've just applied Bayes' rule. So we have P of zn given theta t. This isn't written here explicitly. But we should also have y of n here in this condition. So here we just applied Bayes' rule. It's pretty easy to see that this is the joint probability of the two, and then to get the conditional probability of z of n, we just sum over all the possible k's. So we've done this kind of thing many times. By the way, this pi parameter, this comes from the fact that we're using a categorical distribution as the prior for z of n. Okay, so that's our E step. Pretty easy, especially easy because z of n is a discrete value. So we can just explicitly evaluate this term, this numerator, and then sum them up. This denominator, and then sum them up and divide it by the numerator. By the way, this, in the case of clustering, this value here is often defined as R for responsibility. Okay, so that's our E step. Here's our M step. So in our M step, we need to maximize our Q function. Here's our Q function written out. Notice that we've thrown away that H term. We've thrown it away because, again, it doesn't depend on theta. So we don't have to worry about it in the case of optimization. In the textbook, we're again using this expectation notation. So let's be really explicit about this. This is the expectation imagining that z of n is distributed according to q of n t, which is equal to sum over all the possible values of z of n of qt z of n times this thing we have in the brackets. Okay, so I'm not going to spend too long on this. I'll let you go through the textbook, but very briefly, in order to, what's the likelihood of z of n? We have the categorical distribution for z of n and the conditional distribution for y of n. Those are just the categorical distribution and normal distribution, so we've just written them out here. And we're using this Zn to select which term we're ending up with. Now we can write out this expectation explicitly. We did it like this. Expectation of z of nk is kind of a tricky way of writing q of nk. I don't know why the textbook likes to use that notation, but that's what they're doing, which, by the way, is the same thing as r of nk. So notice that all of those things are the same. And then here we've just written out our terms here. Okay, so this is a big expression. Notice that we have two sets of parameters that we have to optimize over. That's our theta. We have our categorical distribution probabilities, we have our means, and we have our covariance matrix. So all those three things we have to optimize over. Notice, though, that it's pretty easy to do this derivative now. So here we just have a sum over a bunch of stuff involving pi k. So we have to take, if we want to optimize pi k, if we want the partial derivative with respect to pi k, we just need to look at this term, and it's just a sum. If we want the partial derivative with respect to mu, it's just this quadratic thing here. and same thing goes with sigma. So I'm not going to do the derivative here. I recommend doing it as an exercise. It's not too hard at all. And once you do that and set it to 0, you get these expressions here, which are pretty intuitive. Now, so once you actually apply this, it's going to have this kind of iterative approach that we're used to seeing for clustering algorithms. So we start here where we've defined our mu and sigmas as some arbitrary initialization. Then at each iteration of EM, they're going to evolve and end up as these respective Gaussian distributions over these two clusters. So, by the way, this probably looks very familiar if we've seen k-means clustering, for example. K-means, one way to think about k-means is that it's a type of EM. One thing that's different between kind of the traditional k-means clustering algorithm and what we're showing here is that k-means tends to, or k-means, the traditional k-means explicitly assigns each example to a specific cluster at each iteration. So you can think of that as a hard EM, that is a variant of EM where we, instead of using the responsibility as this probability, we just pick whichever is greatest and set that to 1. Generally, it's more principled to use this responsibility, although it's done in practice relatively often to use the kind of hard EM variant. You can think of that as a variant of EM. Another thing about k-means is it's generally using squared error rather than writing out a Gaussian distribution. We've said that squared error and Gaussian distributions are very related to one another. Squared error is identical to a Gaussian distribution with a diagonal covariance matrix. So one thing that's nice about thinking about k-means as EM is it makes it very obvious why this idea makes sense of using a Gaussian distribution with a non-diagonal, necessarily, covariance matrix, rather than defining it as squared error, which is equivalent to requiring that covariance matrix to be diagonal. Okay, so that was our example, EM for a mixture model. Again, all we did was we defined our E step and M step respectively using this specific probabilistic model that we defined in the mixture model case. Okay, let's do another example. In this case, we're going to look at the example where we have some vector and we imagine that this vector is generated according to a multivariate normal distribution with some mean and covariance that are unknown. So this is what we're going to try to learn using EM, this mean and covariance. But we imagine that we observe some of the values in this vector for each example, but we don't observe some other ones. So this could be commonly the case if you have a bunch of tests that were done on each patient. Let's say you're doing some kind of diagnosis, but for whatever reason, the doctors didn't do some of the tests. or you're doing some kind of survey and for whatever reason, some of the questions weren't offered to some of the respondents. Notably, we're going to assume here a missing at random assumption, which is that we're going to imagine that whether or not a given vector value is missing doesn't depend on anything else in the problem. So we're imagining it's just missing for nothing that has to do with anything else. Just someone dropped the data. So of course, very often in practice, that's not the case. For example, in like a clinical setting, if a test was performed, often the test was performed because the patient had some observable symptoms that encouraged the doctor to make that test, or they didn't have the symptoms, so the doctor didn't do the test. But let's assume now that the data is missing at random. And also notably, it's not the same value missing for every example. So we might have another vector here. So if this is example 1, example 2 might have these present, but not those two. Of course, we'd have a lot of, if we never observed this third entry here, we'd have a lot of trouble learning anything about it because we'd have zero information. But we're going to assume that that's not the case. Now, just intuitively, we could imagine that we ought to be able to do a reasonably good job at imputing these missing values, because we should do a reasonably good job assuming there's some correlation structure within the data. So for example, let's say value 1 and 3 are correlated in practice, then based on the values on the examples where both are present, we should be able to learn that that correlation is the case. And then based on that, in this example number 1, where the third entry is missing, we can use that correlation and say, okay, feature 3 is probably identical to number 1, or we can figure it out what it is based on number 1. So that's the idea of this learning a multivariate normal with missing data case. So let's define this a little more precisely. For each example n, we're going to define yn as the present data values and zn as the missing values. And we're imagining that they are jointly distributed according to this normal distribution. Now the textbook does something I don't really like, which is that it overloads notation here, and it uses yn interchangeably as this, as both, as well as just the present one. Not quite sure why they do that, but in the lecture here, I'm going to try to use yn prime. Prime meaning both, yn not prime meaning just the present ones. If we wanted to draw this in graphical model format, it might look something like this, where here we have, let's say we have a length 4 vector, like we defined here, and we have y1, y2, y3, and y4. There's kind of dependence among all of them because we have this, we're imagining they're generated from this multivariate normal. So assuming that this covariance matrix doesn't have a lot of independencies represented in it, we kind of have dependence among all of our variables, and among those, for a given example, some of them are observed and some of them are not observed. So I've done the observed ones in the blue shading. Okay, let's see what happens when we apply the EM algorithm. So we have two steps. We have the E step and the M step. Let's start with the E step. In the E step, we need to derive the probability of the hidden variables given the observed ones for a specific value of our theta. Again, theta here is our mean and covariance values. I'm not going to do this derivation, but we've actually done this before. This is, to get these, we're using the Bayes rule for normal distribution expressions that we came up with a couple of lectures ago. And it turns out if you use those, you end up with this, which is that we find that z of n is distributed according to a multivariate normal with these two parameters here. We're using m and capital V because these are kind of empirical mean and covariance rather than a mean and covariance that we're learning in our parameters. That's kind of a convention. We use the non-Greek letters for what we get from our sample. But note that m and v, they are mean and covariance values of this particular normal distribution. Turns out that it ends up equaling this. Here we've defined h subscript to be the mu for just the hidden values. Likewise, sigma VV is the submatrix. If here's sigma, and we have some visible and hidden, then sigma VV is just this visible submatrix. That's supposed to be VV, not W. And then likewise, this one is VH, HH, and so on. Turns out we can write them down like this. I'm not going to go through it directly, but it's relatively just some matrix algebra to get our m and v expressions. So that's our E step. That gives us this probability distribution over z. Now notice that because z is a continuous random variable, again, we can't just write down explicitly its probability distribution. We had to observe that z follows a normal distribution and give the parameter of that normal distribution. We can't explicitly write it down because it's some continuous thing. It has kind of an infinite number of points to write down the probability density function explicitly. Okay, that's our E step. How about our M step? So in our M step, we have to define our Q function, and we're going to maximize it in theta. Now, for whatever reason, the textbook here is using theta t minus 1 here, and we're going to derive theta t instead of before we started with theta t and derived theta t plus 1. I don't know why they swapped that notation, but it doesn't make much of a difference. Here is our EM expected log likelihood term. And again, I think it helps to be explicit with this expectation. This is the expectation assuming that z of n goes according to that normal distribution that we defined on the last slide in the E step, which equals I should write this as a integral of normal of Zn given m and v times that thing in the brackets there. Okay, so that's our that's the value of our Q function. We have to do a bit of math and algebra to figure out how to optimize this and take its derivative. I'm not going to do this explicitly. It's not too hard. It's in the textbook. I encourage you to take a look. But once we do the algebra, we get something that looks like this. So we did a bunch of steps of algebra here, and we got this thing. We have a term that depends just on sigma, a constant term, and we have this thing, the trace. Remember, the trace of a matrix is just the sum of its diagonal entries, times sigma times this thing. So notice that this thing, this term here, is the only one that depends on the E step, because this expectation is still of Zn following that normal distribution. We define an E step. We can define this thing here with a bit more algebra. We get this thing, which is the expectation of yn. This y is the full version, not just the observed ones, times expectation of yn. Or sorry, it's this term involving the expectation yn times yn plus this thing mu mu minus a term involving the expectation of just yn itself. Now these two expressions, it's not too hard to evaluate those given that you know what the parameters of the normal distribution are. Specifically for this term here, expectation of yn, it's pretty easy to show that that thing equals mn. That is the mean value of that normal distribution. And of course, so that's just for the hidden variables, the hidden values. For the observed values, expectation of yn is just that observed value. That's not hard to see. With a little bit more math, you can figure out what this term is too. That's not too hard. The upshot of all of this is that given that we know from the E step that z of n is distributed according to this, we can pretty easily plug in those mean and variance values here, and we end up getting something that's pretty easy to take the derivative of. I'm not going to do that part as well, but it's pretty easy to show. We get the following updates for our m step. Once we've taken the derivative and set it to 0, these should look pretty familiar when we've seen the normal MLE update for a multivariate normal. It's defined like this. Again, these two are easy to define according to the m and v parameters we defined in the E step. It's worth convincing yourself that this isn't quite what you'd get if you just took each hidden variable and plugged in its expected value. Doing that ignores the uncertainty in the value. So that's what you'd get if you did hard EM, kind of more similar to what we do in sort of traditional k-means clustering, would be to just plug in the most likely value for each of the hidden YNs, or for each of the hidden ZNs, and then do our update assuming they're observed. This does something, EM this way does something a bit more principled, which is to account for the uncertainty in each value. Turns out to give you better results. Okay, so that's it for the EM algorithm. As I said, the EM algorithm comes up very often. It comes up when we have some kind of probabilistic modeling framework where we have hidden unobserved variables. That turns out to come up quite a lot. And in that case, when we can work out what the EM algorithm amounts to for a given problem, it tends to be very effective, both very fast and it tends to behave very nicely, be very easy to debug. Our Q function always decreases from iteration to iteration. We don't have to worry about divergence. We can easily debug when we made a mistake. So it's used very often in practice. The downside, of course, is that for each new problem, often we need to derive what the E and M steps amount to, which can be a bit of work on the kind of mathematical side. But once we've done that work to derive the updates, again, they tend to be very fast and very well behaved.